last time we discovered that there were several different ways of taking linear combinations of the states to come up with perhaps handier states. These are also states. There are an infinite number of possible states you could use. For example, if you had a pendulum with theta and theta dot, you could use theta plus theta dot and theta minus theta dot, or you could use theta and theta dot, or you could use any linear combination of those, and those two, the new linear combinations are also states. And you only need one system of states, but some sets of states are handier than others. For example, the one we looked at that had the eigenmodes uncoupled was handy because the eigenmodes are uncoupled. So our goal is actually to control something. So what we're going to do is we're going to be monitoring the output of a system. We're going to see what it's doing, and based on what it's doing, we're going to adjust the input of that system to get it to do what we really want it to do. And so we need to figure out how we could actually try and set the eigenmodes to any eigenmode we like. We don't like being stuck with particular eigenmodes because in some cases it might be unstable. Like, for example, if one of the eigenmodes had a positive real part, that would tell us that we're going to have e to some positive number times time as our solution, which means that it gets bigger and bigger and bigger as time t goes toward infinity, which means it's probably going to break, okay? And so we want to avoid those kind of situations. They're unstable. It's like when you saw the cart wanted to fall over. And we don't want it to fall over, we want it to stay upright. So we're going to adjust what we send to the motors based on how we see it falling. And so we're going to kind of make it fall up instead of down. So in order to do that, we need to find out whether it's even possible. And second of all, because it's not always possible, suppose if you didn't even have any inputs, then it wouldn't be possible. And maybe your input doesn't affect enough of the states, and then it wouldn't be possible. So what we have come up with is a thing called the controllable canonical form. It also is known as the first companion form. And if we can transform the system that we start with, x dot equals ax, into this form, then we are golden. We can set the eigenmodes up however we like. And we can make all the s values anything we like. And so we'll be very happy. But if we can't do that, then we won't be too happy. We'll have to punt and come up with a new input or something. So basically, what I want to do is introduce you to this controllable canonical form so you can see what it looks like. Often when we start out writing mechanics state equations, they even often turn out to be in this form to start with, but not always. So let's look at the controllable canonical form. Generally, we start from the transfer function, which was c si minus a inverse b plus d. And this transfer function is a numerator polynomial in S divided by a denominator polynomial in S. Now you have to remember that multiplication by S is like differentiating in time. So what we do is we take this numerator polynomial of S, like you see on my second line of my notebook here, and you multiply the whole line by W of S over W of S. So we haven't changed anything because W of S over W of S is just 1. So essentially we multiply by 1 in this nice form. And then we say, suppose W of S was such that the Y of S, which is on the numerator of the left-hand side of the equation, made equal to this denominator on, the numerator on the top, on the right-hand side of the equation times W of S, so Y equal to that numerator times the W of S, and then the denominator, U of S, would equal the denominator of the right times W of S. And those are the two equations we have right down here. And then if we take and solve the equation on the bottom for s to the n w of s. And then we'll have u of s minus all those other terms. And we draw a block diagram for it. It will look just like this diagram you have here on below the equation. And remember, each of those s w of s basically means differentiate the w of s. So what we have is, when you go backwards through an integrator, you're differentiating. So on the right, we would have w of s right over here. This would be w of s. And this guy over here would be the s to the n w of s. And then what we do is we assign this w of s to be the first state variable, and then the next one on the other side of the integrator is sw of s, and you keep going all the way out until you run out of integrators. And you'll have n integrators if there's it's an nth order state equation. And so then you can say, well, what is s to the n w of s? Well, you just use this equation right above the diagram, and you notice it's 1 times u of s, and it's equal to all these little coefficients, a1 a n minus 1 times s to the n, times s to the n minus 1 w of s. That's what this one is here, s to the n minus 1 w of s. And so on, and you just make that equation up using your block diagram algebra, and we've got a very nice little block diagram here. The thing that's so special about this is you can see that all the coefficients of the characteristic equation, those are the a's in this in the denominator. The denominator equals 0 of the transfer function. That is the characteristic equation. And if we could change all those a's to anything we want, we could actually control this to have any roots that we want, and those roots are the eigenvalues. And so how could we do that? Well, if you look at these things, basically what I could do is take a little bit of each of these state variables and feed it back into the input. Just take a little bit of the w of s, that's the x, x1, and add it into u of s. And basically that's just like changing all these a's in this block diagram. So if you take that block diagram, you can also make a matrix equation out of it, and when you do it, it looks like this. If you look at the x1 is equal to, or x1 dot is equal to basically right here, x1 dot would be 0 times x1 plus 1 times x1 dot. You can see they're just, it's just going back, becoming one higher derivative every time, which gives you this nice ones on the superdiagonal, zeros above that. And then everything on the bottom below the diagonal is 0 except for the last line, which has all those coefficients from the characteristic equation. And so this is known as the controllable canonical form, and if we can put it in this form, we can control it. If we can also know what all the state variables are and get them. In other words, I'm kind of assuming from my feedback that I could actually measure the theta and the theta dot, and I could use that measurement to figure out what I want to put in for u. And that's not always the case, but we'll address that in another video.